We are working with solving absolute value inequalities. It says you know that when solving an absolute value equation, it's possible to get two solutions. Here you will explore what happens when you solve absolute value inequalities. Determine whether each of the integers from -5 to 5 is a solution of the inequality. The absolute value of x plus 2 is less than 5. Write yes or no for each number in the table. If the number is a solution, plot it on the number line. So x is equal to -5. If I plugged in -5, that would give me a +5 plus 2, which would be 7. But 7 is not less than 5. So we are going to write no. Now let's try -4. The absolute value of -4 would be +4, and 4 plus 2 is 6, which is not less than 5. -3. -3, when you take the absolute value, becomes +3. Oops, and 3 plus 2 is 5, but it's not less than 5, so it is still no. Then if we did -2, the absolute value of -2 plus 2, that would come out to 4. And 4 is less than 5, so we are going to write yes. And it asks us to plot -2 on the number line. -1. Absolute value of -1 is +1. 1 plus 2 is 3, which is less than 5, so that is also yes. 0. The absolute value of 0 is 0, plus 2, which is 2, and that is less than 5. If we did the absolute value of 1, we'd get 1. 1 plus 2 is less than 5. If I did the absolute value of 2, 2 plus 2 is 4, which is less than 5. The absolute value of 3 is 3. 3 plus 2 is 5, but that is not less than 5. So no, no, and no. For the next one, it says determine whether each of the integers from -5 to 5 is a solution of the inequality. They've switched it to say greater than 5, and then write yes or no for each number. So we have the absolute value of -5 is 5, 5 plus 2 is 7, and that is greater than 5. The absolute value of -4 is +4, plus 2 is 6, which is greater than 5. -3 would be +3, plus 2, that's 5. Is 5 greater than 5? No. -2 would come out to +2, plus 2 is 4, but that is not greater than 5. Then we've got -1. The absolute value of -1 is +1. 1 plus 2 is 3, which is not greater than 5. 0 plus 2 is not greater than 5. 1 plus 2 is not greater than 5. 2 plus 2 is not greater than 5. 3 plus 2 is equal to 5, but it is not greater than 5. 4 plus 2 is 6, that is greater than 5. And 5 plus 2 is 7, which is greater than 5. State the solutions of the equation, the absolute value of x plus 2 equals 5, and relate them to the solutions you found for the inequalities in steps A and B. Well, the solutions would be x is equal to -3 or x is equal to +3. And the way that we find that, or is related to the solutions we found in A and B, is those are the only two values that weren't true in either situation. If x is any real number and not just an integer, graph the solutions of x plus 2 is less than 5 and the absolute value of x plus 2 is greater than 5. We know that it can't be on 3, but we know that that's what makes it equal. So those are our open circles or open points. And for the one that said less than 5, it was all the points in between. For the one that said greater than 5, it pointed out in the opposite direction. It's possible to describe the solutions of the absolute value of x plus 2 is less than 5 and the absolute value of x plus 2 is greater than 5 using inequalities that don't involve absolute value. For instance, you can write the solutions as x is greater than -3 and x is less than 3. Notice the word "and" is used because x must be both greater than -3 and less than 3. How would you write the solutions for x plus 2 is greater than 5? This is an "or" problem because they're headed in different directions. So we would say that the solutions are x is less than -3 or x is greater than 3. Describe the solutions to the absolute value of x plus 2 is less than or equal to 5 and the absolute value of x plus 2 is greater than or equal to 5, using inequalities that don't involve absolute value. So we're just writing those solutions. The only thing that would change is instead of saying less than or greater than, we're going to have the other symbols. So I'm going to split this in half here. For this first one, we would say x is between -3 and 3, but it could be equal. And for the other one, this is the "or" problem, so we would say x is less than or equal to -3 or x is greater than or equal to 3. We're just changing those symbols to have that equal sign underneath. You can use a graph to solve an absolute value inequality of the form f of x is greater than g of x or f of x is less than g of x, where f of x is an absolute value function and g of x is a constant function, meaning just a number. Graph each function separately on the same coordinate plane and determine the intervals on the x-axis where one graph lies above or below the other. For f of x is greater than g of x, you want to find the x values for which the graph f of x is above the graph of g of x. For f of x is less than g of x, you want to find the x values for which the graph of f of x is below the graph of g of x. So That's a lot of language basically saying we're going to graph the inequality and then we're going to graph the constant in a straight line, and we're looking for whether it's above or below depending on greater than or less than. So it says in A, the absolute value of x plus 3 plus 1. And we learned earlier in our lessons that if it has this piece inside the absolute values, that it shifts the function one way or another. Since it should say x minus h, so since it says x plus 3, we're going to move to the left 3, and then this value moves it up 1. So you can see they started their vertex of their absolute value function at the point -3, 1. And then it doesn't have any of those values in front here, so it's just a slope of 1. And you can see that they've drawn their absolute value function. Then they've taken this number 4 and they've graphed that straight line up here at 4. And we are looking for where it is greater than 4. So we're looking at where the absolute value is above. So it says the inequality is of the form f of x is greater than g of x, because it has the greater than symbol. So determine the intervals on the x-axis where f of x lies above g of x. So we're talking about this piece here where it's above and this piece here where it's above. So it says the graph of f of x equals x plus 3 in the absolute value bars plus 1 lies above the graph of g of x equals 4 to the left of -6. So you can see right here at -6, it starts to go above that line, and to the right of 0. So as we get closer to 0 on the x-axis, it's going to start to go above that line as well. So you can see they've written it out, and they said, so the solution is when x is less than -6, so our x values are lower than -6, we're trailing out to the left, and when x is greater than 0, we're moving out towards the right. Now it's our turn. The absolute value of x minus 2 minus 3 is less than 1. The inequality is in the form f of x is less than g of x. So to determine the intervals on the x-axis where the graph of f of x lies, we're looking for below because it's less than. And we also need to graph it. So we talked about how this is going to shift it. So our vertex should be at the point +2, -3. Remember, it's x minus h and then plus k. So we're looking for the opposite of -2 as a +2, and then we take that -3. It also has a slope of 1, so we're just going to draw those straight lines coming out of there. And for the other, and we also need to graph +1, and we are looking for where it lies below. So that is between the x value 2 and the x value 6. So the solution is when x is greater than, -2 and +6. So between -2 and +6. In number 3, it's asking us to look back at part A. It says, suppose the inequality in part A is x plus 3 in absolute value plus 1 is greater than or equal to 4 instead of just being greater. How does it change the solution? Or how does the solution change? It would change the solutions to now include those endpoints. So instead of x is less than -6, we would say x is less than or equal to -6. And instead of x is greater than 0, we're going to say x is greater than or equal to 0. In part B, what is another way to write the solution x is greater than -2 and x is less than 6? This is an and, so it can be rewritten in that shortened version where x is between -2 and +6. Suppose the graph of an absolute value function lies entirely above the graph of a constant function. So it would look something like this. The absolute value, the whole thing is above that horizontal line. What is the solution of the inequality? If it says greater. So in that first one, if f of x is greater, then the solution would be all real numbers because all x values are above that number. But what about for f of x is less than g of x? Are any points of the inequality less than the constant function? No, because they're all above. So for f of x is less than g of x, there is no solution. Number 6 says solve the absolute value of x plus 1 minus 4 is less than or equal to -2 graphically. It did not give me any graph space, so I just added one in. If you want to use graph paper, you can. If you want to just do a sketch, that's fine too. Up to you. We're going to start with the point -1, -4. Remember that inside the absolute value, you have to switch it to the opposite. So -1, -4. Then we'll draw our V shape coming out of that. Then we also need to graph our horizontal line at -2. And we are looking for where it is less than or equal to. So our inequality is below -2 in these locations. But remember, we solve it with the x values. So that x value is at -3 and +1. So we're going to say that x is between -3 and +1. I included those equal to in the symbol because it says equal to up here. Solving absolute value inequalities algebraically. To solve an absolute value inequality algebraically, start by isolating the absolute value expression, just like we did when we were solving absolute value inequalities. When the absolute value expression is by itself, on one side of the inequality apply one of the following rules to finish solving the inequality for the variable. If the absolute value is greater than a and a is a positive number, then we're going to look at when x is less than -a or when x is greater than a. So we're taking it out of those absolute value bars, and we're doing similarly to solving inequalities where we change them to the opposite number. But when you do that, you also have to change the symbol to the opposite symbol. If the absolute value of x is less than a and a is a positive number, then you're going to say that it's between -a and +a. So solve the inequality algebraically. Graph the solution on a number line. They start in A by isolating or making the absolute value bars by themselves. So they subtract 15 from both sides. and that gives them that 6. Then because it's greater than A, we're going to make one say less than the opposite, so less than -6, and then greater than 6. So then they solve them both separately. They subtract 4 from both sides. That gives them that -10. Then they have to divide by -1, which gives them +10. But remember, when we multiply or divide by a negative, we have to switch that symbol around. For the other inequality, they subtract the 4, and that gave them 2. They divide by -1, that gives them -2, but they flip the symbol around. So x is greater than 10, or x is less than -2. And that's the solution to this absolute value inequality. In B, we're going to start by adding 10, which gives us +8. Since that's in the less than situation, we have an and problem. So x plus 4 is greater than or equal to -8 and less than or equal to +8. Then we're going to subtract 4 from both sides. That's -12. And this one would be 4. So the solution is x is greater than or equal to -12 and less than or equal to 4. So we're going to put a dot that's closed on -12 and a dot that's closed on 4 and graph all the values in between. Seven, in part A, suppose the inequality where 4 minus x in absolute value plus 15 is greater than 14 instead of greater than 21. How would the solution change? Explain. We would still start by isolating the absolute value, so it would look like this. We would subtract the 15, and we'd have 4 minus x in absolute value is greater than -1. The whole point of absolute value is to make everything positive. So then all of these values, no matter what you put in for x, will be greater than negatives. So at this point, we can stop. You don't have to continue because all real numbers work. In part B, suppose the inequality where x plus 4 is minus 10 is less than or equal to -11 instead of -2. How would this change? So again, we would start x plus 4 needs to be isolated. So we would add the 10 to the other side. That gives us the absolute value of x plus 4 is less than or equal to -1. Since absolute value is always going to be positive, the lowest it can be is 0. Is 0 less than or equal to -1? No. So this has no solution. Solve the inequality algebraically. First, isolate the absolute value. So we're going to divide both sides by 3. When you have the greater than case, it is an or situation. So we turn this into x minus 7 is greater than or equal to 3, or x minus 7 is less than or equal to negative 3. Then we have to add 7 to both sides. X is greater than or equal to 10, or x is less than or equal to 4. For 10, it is already isolated, but it's a less than problem. Lessons are and problems. I don't necessarily love doing it as two separate inequalities if it's an and, so I'm going to write it in the compound inequality format to begin with and show you how I would solve it that way. So I have 2x plus 3 in the middle is less than 5 but greater than negative 5. Remember, we need both. And then I would start by subtracting 3 from all sides. That would give me negative 8 over here and positive 2 on the right. Then I would divide all sides by 2, and I would end up with x is less than 1 or greater than negative 4. So then I'm going to put an open circle on negative 4 and on positive 1, and I'm going to draw my line in between. Solving a real-world problem with absolute value inequalities. Absolute value inequalities are often used to model real-world situations involving a margin of error or tolerance. Tolerance is the allowable amount of variation in a quantity. A machine at a lumber mill cuts boards that are 3.25 meters long. It's acceptable for the length to differ from this value by at most 0.02 meters. Write and solve an absolute value inequality to find the range of acceptable lengths. Identify the important information. The boards being cut are 3.25 meters long. The length can differ by at most 0.02 meters. Formulate a plan. Let the length of a board be L. Since the sign of the difference between L and 3.25 doesn't matter, take the absolute value of the difference. Since the absolute value of the difference can be at most 0.02, the inequality that models this situation is the length minus what the length is supposed to be can be less than or equal to 0.02. And now we solve. So they isolate the absolute value, which was already done. It's a less than or equal to, which turns into an and problem. They separate it out. If I were doing this by myself, I would write it like so. And I would solve it in one long problem instead of doing two. I would add 3.25 to both sides, all sides. And that would end up with the length is between 3.27 and 3.23. So the length has to be greater than or equal to 3.23 and less than or equal to 3.27. then they would write it in the compound inequality at the end, whereas I already have it in a compound inequality. The choice is up to you how you solve it. I just like one version because it puts it in the format I want in the end anyway. The bounds of the range are positive and close to 3.25. So this is a reasonable answer. The answer is correct since 3.23 plus 0.02 equals 3.25. And since 3.27 minus 0.02 is equal to 3.25. 11. A box of cereal is supposed to weigh 13.8 ounces, but it's acceptable for the weight to vary as much as 0.1 of an ounce. Write and solve an absolute value inequality to find the range of acceptable weights. So let's say the weight of the actual box is W, but we know that it's supposed to be 13.8, so we're trying to find the difference. And then if it's more or less, it doesn't matter because we're going to make it absolute value in the end. So we're going to turn it into that distance that's positive. And it says it can vary as much as 0.1, meaning it can be equal to 0.1 or it can be less than that. It can be closer to the actual amount. Since this is a less than or equal to problem, it is an and situation. So I'm going to change it to say W minus 13.8 is less than or equal to 0.1 or greater than or equal to negative 0.1. Then we will add 13.8 to all sides. And we will have our solution. It has to be between 13.7 ounces and 13.9 ounces. Describe the values of x that satisfy the inequalities. Absolute value of x is less than a, and where absolute value of x is greater than a, where a is a positive number, a positive constant. For the less than case, that is an and situation. So the solutions are x is between negative a and positive a. For the greater than case, that is an or situation. So the solutions are x is greater than a or x is less than negative a. How do you algebraically solve an absolute value inequality? Step 1, isolate the absolute value. Step 2 is to write the compound inequality with and or that doesn't have absolute value. And finally, solve for x, or solve for the variable. 14. Explain why the solution of x, the absolute value of x is greater than a, is all real numbers if a is a negative number. Absolute value is always positive. So it is always greater than a negative. Always, meaning no matter what value you put in there. So all real numbers. 15. How do you solve an absolute value inequality graphically? We start by graphing each side separately. Then, depending on whether it's greater than or less than, we have to look at where it touches or where it crosses. To put it in some math lingo, use the symbol to determine, so we're talking about the greater than or less than symbol, determine the interval for x, meaning the solutions, where the absolute value function, that V-shaped function, is above or below the constant function, that straight line.